Good morning, everyone. For everybody to get in here. We've got more coming in. Can anybody speak up and let me know whether they hear me? I've had some.
Yeah, we can hear you.
Yeah.
I've had audio problems.
Yeah,
with
I can hear you.
me, or y'all hearing, or me hearing y'all. So now I've confirmed both. Thank you for that. Still got more people. More people, more people. Anybody have any questions while we're waiting for everybody to come in? No questions? That's good. All right. Let's see. No questions now. All right. Well, it looks like we've got 19 people. That's pretty close. So I guess we'll go ahead and go. We did, I've essentially finished with chapter 5, but I think I'm going to go ahead and jump into chapter 6. I am, but I'm going to go ahead and do a velocity problem where you basically drop in an object and have air resistance on it. So I thought I'd work one of those. It's sort of like the last thing that your book covers in chapter 5. And then I'm going to go into talking about gravity, which is what chapter 6 is about. So we'll be able to knock out chapter 6 next week as well. I'll go ahead and put the homeworks up for chapter 6 as well, which I think they're already available. I just got to make sure the dates are right. I think they are. I think I set everything to be the correct dates up until chapter 9 or even 10. So if you guys have any questions, make sure you ask me. I'll go ahead and start off with this derivation of basically free fall with air resistance. So remember, free fall is supposed to be an object falling and the only force acting on it is gravity. And when that occurs, we found that the acceleration was 9.8 meters per second every second. Well, this is a different case. And what we find is that the drag force sort of has two criteria. That really does not look good, does it? A little better. Not a whole lot, but a little. Okay, so the drag force has two criteria. It's proportional to V or proportional to V squared. The V squared is definitely more common when you're talking about like submarines and water, more viscous fluids. But there's also at higher speeds, the V squared kicks in as well. So we're going to just attack this case. And you'll see once you take your differential equation class, or if you already have, you'll see that this is one of the first differential equation problems you'll solve. So we're going to just attack this one and we'll go from here. So what we have is an object of mass M that has acting on it a force in the positive direction equal to mg, and then a force in the negative direction, which actually changes. It's not a constant force. It's dependent on velocity. Yes, mastering physics is where that homework is. Someone asked me that. Yeah, gotcha. So the other force in this case is initially it'll be essentially 0, but then over time it's going to grow and it's going to be basically b times the velocity or the speed basically. Now you can look up, there's formulas for this and stuff like that, and basically this b depends on the cross-sectional area. So for instance, if you dive head first, your cross-sectional area sort of looks like this. Something like that. So there's your shoulders, there's your chin, say, sticking out, the back of your head, something like that. So that's your cross-sectional area. And if you were to say, I really want to survive this fall to the earth, then your cross-sectional area would be better, looking like this. Like an X chromosome, Okay, so that larger cross-sectional area is really going to be your friend. And believe it or not, yeah, you need to do a belly flop or a back flop if you want to try to survive a fall from an aircraft, just because that increases your cross-sectional area. Obviously, that's also why parachutes work, because that turns a cross-sectional area like this into a cross-sectional area like this. So that's really the big deal. So let's go ahead and talk about our Newton's second law. So Newton's second law in the y direction is going to be mg minus bv is equal to m dv dt. Remember, it's a, but a is really dv dt. So what we're going to try to do now is we're going to go ahead and I'm going to divide through by m just to get rid of that that m and everything. So if I divide this side by m and I divide this side by m, what I'll get is, the person came in, what I'll get is g minus b over m times v is equal to dv dt. Now I can rewrite this in a way that's helpful. I can write the dv, and we'll try to write it a little bigger to see if that doesn't make the image look a little better. dv over g minus b over m v is equal to just plain dt. Now, this is called a separable differential equation because we've been able to separate it basically and put the variable that relates to the dv under the dv. And I'm going to integrate this from v equals 0. I think I'm using my marker that's dead, to v of t, which we can just save some time by just calling it plain v as opposed to v of t. But occasionally I'll put the v of t in there just to remind you that we're ultimately getting the v as a function of time. And you can definitely see that from this range of integration, which is t equals 0 to t. So if we let u equal g minus b over m times v, then du is equal to negative b over m dv. So all I really got to do is multiply by negative m over b and by negative b over m, and this left-hand side will become negative m over b integral du over u. And of course, the integral dt is just going to be t, so I'll just put that over here to the side. And the range of integration is actually in terms of v, so I'll just leave that b for right now. Now, if I take the integral of this, that's just the ln, the natural logarithm. So I'm going to go ahead and write ln of g minus b over v, or b over m times v, and that's evaluated from v equals 0 to v of t. I'm going to go ahead and multiply this, both sides of the equation, by negative b over m. So this will equal negative b over m times t. And now I will complete this portion by evaluating this log at these two values, and I will get the natural log of g minus b over m v of t over just plain g, because when v is 0, we get that. Now I'm going to make mathematicians squirm by saying I'm going to raise e to this power and set it equal to e raised to this power. And what you end up getting is whenever you raise e to the natural log power, you just get the argument back. So I'm going to get g minus b over m v of t over g is equal to e minus b over m t. So now that we have that, we can multiply through by g, and I'll get g minus b over m v of t is equal to g times e to the negative b over m times t. I can then pull this to that side and that to this side, and I'll get b over m v of t is equal to g times 1 minus e to the negative b over m times t. We're getting closer and closer now. So finally, I can say that the velocity as a function of time is going to be equal to mg over b times 1 minus e to the negative b over m t. You can see when t is equal to 0, then this becomes e to the 0, which is 1, and 1 minus 1 is 0. So the initial velocity is going to be 0. That's what we set up by saying v is equal to 0 there. Okay, so that makes some sense. And what we see is t goes to infinity. This is a negative exponent, so that means it's really 1 over e to the b over mt. So as t gets larger and larger, this number gets smaller and smaller and will eventually approach 0 because it's in the denominator. And as the denominator goes to infinity, the whole fraction would go to 0. So what you see is it should asymptotically approach the velocity mg over b. So make a function of time like this and make v this way, then it's going to start at 0 and it's going to have a velocity mg over b as sort of an asymptote. And you might recognize that as the terminal velocity, and that's exactly what it is. You can see from the original Newton's second law that basically when mg is equal, or mg over b is equal to v, so you can see v is equal to mg over b, that force becomes 0. So that's really why we have a terminal velocity. V terminal is equal to mg over b. And you can see, like I said, if I plug in mg over b right there in that original Newton's second law, the mg over b will cancel out the b in the bottom with the b on the top, and I have mg minus mg, which is just 0. Okay, so just to clarify that, Newton's second law was mg minus b v equals m dv dt. That's Newton's second law, and this is where I started to work it out. So I just wanted to rewrite it again so you can see. Does that make sense to everyone? You can even determine basically the amount of time it will take to get to a factor of, say, 1 over e of the terminal velocity. So you could say, for instance, right along here somewhere is a velocity mg over b e. And that is sort of a characteristic time. And I think you can see if you put in that, for the velocity mg over b times just the plain base e, you can solve for the time and get that. So let's give that a try. Let's say I want to know when the velocity becomes mg over b e, which is 1 over e times b terminal. Okay, so let's do that. Let's write on this side, we'll say mg over be is equal to mg over b times 1 minus e to the negative b over mt. We can see now that the mg over b's cancel out, and I'll get 1 over e is equal to 1 minus 1 over, notice how I write it this time, e to the positive b over mt, like that. Now I can get rid of these parentheses and just think, okay, well, I want all the e's on one side, so I'll pull this over to here, and that'll become plus. So I have 1 over e plus 1 over e to the b mt is equal to 1. So now I can just try to solve for t. The way I might do that is notice these two have to sort of be added. That's a bit of a problem. What's a better way? Actually, I think that's good that way. I could get a common denominator by basically multiplying by this by E B over MT in the bottom, and multiply this by E in the top and bottom. So let's try that. I'm going to go this way, which is kind of weird for me writing it this way. So I'll say EB over MT over EB over M. Since you're multiplying, you're going to have EB over MT times E to the 1 power. So when you multiply two things with the same base, you add the exponent. So BMT plus 1 would be up here. And that's the denominator that each of them will have. But on this side, you'll have plus just E to the 1. And that's equal to 1. So in principle, we can now get this by saying, let's take the log of both sides. And we know the log of 1 is 0, right? Double check that. We'll say the log of 1, and sure enough, it's 0, like I said. I just didn't want to think it out. I was lazy. So this quantity is equal to 0. So I end up getting E to the B over MT plus E to the 1 over E to the B over MT plus 1 in the denominator is what this side becomes. Because when you take the E, actually, it's not that. Scratch that. We've got that other side equaling 0, so that's something that's sort of helpful. But what I'm going to do now is I'm going to remember that taking the natural log of a division is the same thing as saying the natural log of E to the B over MT plus E minus the natural log of E to the B over MT plus 1. That's all equal to 0. So what that tells you is these two are really equal. So I could say the ln of E to the B T over M plus E is equal to the ln of E to the B T over M plus 1. That basically means that these two things can be equal to each other, which, yeah, I guess that works. So we'll say E to the B T over M plus E is equal to E to the B T over M plus 1. So now I can divide both sides by, yeah, this is not looking very pretty. I could divide both sides by E to the BT over 1, and then you would have everything on here, but you're going to get that T again. So I don't think that works too well. If I divide everything by E to the BT over M, actually what I should have done is 1 over 1 minus E instead of, when I set it to 1 over E, I really should have set it to 1 minus 1 over E or something like that. That would have been a lot easier problem to solve. But anyways, let's see what happens with this. If it works out, great. If it doesn't, that's okay. We've learned something just by me forgetting that it's a 1 minus exponential instead of an exponential. The exponential would automatically come up with a 1 over E. I should have thought of that to begin with, but I didn't because I'm a crackhead. So so what does this mean? Well, this is the same thing as multiplying by E to the negative B T over M. So you could actually distribute that in, and you get E to the BT over M times E to the negative BT over M. That's going to give you just E to the 0. But this one would be e to the bt over m plus 1. This one, on the other hand, would be e to the bt over m plus 1 minus 1. And I ended up getting an identity, so that didn't work. So like I said, what I should have done is solve for when mg over b, when v is equal to mg over b times 1 minus 1 over e. And then it's trivial, because duh, it's when t equals b over or m over b. So everything I did was stupid, boneheaded. When I do that, that's actually 1 minus 1 over e times v terminal. And obviously you can see that occurs when t is equal to m over b. So that's really what I was trying to do. All that crappy calculation was all because I did something stupid and tried to shoot for this, which I should have known better. I don't know what I was thinking, but that that does fix it. Sorry about that. Anybody have any questions on that crazy junk? So I'm going to say all of this right here was stupid of me. Probably several of you in the class already knew that when I was doing it, but you were kind enough not to embarrass me. Thank you very much. Anyways, that's all I wanted to do is show you basically the graph, and then show you that it does include a terminal velocity. Now, if you tried to do two-dimensional motion, you would have a force in the x direction as well. That would be negative b times v. And of course, that would cause the velocity to slow down, but it wouldn't reach a terminal amount because the terminal amount would be 0. It eventually had 0 velocity in the horizontal direction because it doesn't have a force that's constantly fighting it like it did in this case. You had a mg pulling down, a bv pulling back. So those two were fighting. They could come to equilibrium. In the case of basically in the y or x direction motion, you just have negative bv equals m dv dt. So you could actually do that and solve a projectile problem that way. Most of these projectile problems, when you start dealing with air resistance and stuff, are best handled by you write some code to handle the solution of a differential equation and so on. But that's a little bit beyond what we're shooting for here. Now, you can also take and say, well, I do know that the velocity as a function of time, with this part, Mr. Younger got right. So I can set that equal to dx over d or dy over dt, since it was vertical. I can set that to dy over dt and then integrate it. And of course, you'd have to know, for instance, the initial y position, or you just call it y0. But this integral is not necessarily that trivial. So that's something you could do if you wanted to, but I'm not requiring it. Okay. I wanted to mention to you guys too, I put a video up from my D01C class, which is the class that meets on Tuesday and Thursdays. And I put that video up, and it has, I just off the top of my head started throwing out this junk without refreshing my memory. So I got a kind of crappy version of this. So I'm going to refer them to this one, even with all this crap down here that I messed up. But what I did do in that is I introduced an extra credit problem that they can do. So you guys are able to do that as well. And you'll see that in this week's module, week 5, I guess it is, you'll see an extra credit assignment. And the instructions are to see the video that starts with the word finishing space CH5. So if you look at the near the end of that video, you'll see where I introduce an extra credit problem. And it deals with that problem we solved. Remember, we solved the problem where the ball was spinning over your head like this, and you find out how much the string would tilt downward or sag downward as a result of that. Well, I made an approximation there because I didn't expect to travel at such a small velocity. I assumed that the length of the string was the same as the radius of the circle, and you can clearly see that's not the case, right? The length of the string is really the hypotenuse, and then this leg over here on that original drawing would really be the radius of the curve. So it's really supposed to be r times cosine theta. Instead of v squared over r, it should be v squared over r cosine theta. But I just pretended cosine theta was approximately equal to 1 because I'm used to doing it at such high speeds. Well, in their class, I went ahead and I pointed out that that's supposed to be that way. And then I worked it out, and you get a equation that to me looks a little transcendental. It looks like that you're not going to be able to solve it in a closed form. So I gave them 2 ways of solving it and made that as an extra credit. Okay. So if you have any questions on that, by all means ask me, but I've given everybody till Wednesday at midnight of next week to do that as extra credit. And what that counts as is basically a homework problem set, basically 100%, 100 points from a homework problem set. And for instance, if I'd said on your syllabus that you're going to get 2 of the lowest homework grades dropped, if you do that one, you're actually going to get 3 of the lowest homework grades dropped. Okay, so that's how that works. Basically, it'll just take the place of maybe you missed a homework, and you can fix that way. Any questions on that? Yeah, remember, I'm taking a look at the notes from the D01C. And by the way, those notes are in the same place. So the other 241 classes, there's one's a N05B and the other one's a D01C. Both of those are the same class as yours, except they only meet twice a week. So there's more material per meeting than in your meeting, but the notes are in there in that same Google Doc, so you can always look at them if you need to compare. And between the 3 of them, I really have advised people of this. I want to make sure I tell you, if not again, at least for the first time, but you don't need to watch all 3 of those videos. But what I definitely think you should do is like here, I made a mistake, right? But I fixed it, so this part's okay. So if my other class, they remembered I got some trash here at the end. In fact, the trash was really, really ugly. And it's because I did an initial velocity, and that was a bad move. If you start with initial velocity, this all gets even uglier than it is. So if they look at the video from this class, they'll say, oh, wait a second, I remember Mr. Younger used initial velocity not equal to 0 and got some mess on ours, so I'll watch this one. So that's what y'all should do. You should look through, and if there was any examples that I worked in your lectures that you didn't understand, or that maybe I made a careless mistake and you'd like to see it without the careless mistake, or maybe just making the careless mistake made it confusing for you, anything like that. Or if you just need to see it again, I would watch that particular spot. And if it's one that you're comfortable with and you understood completely, then fast forward through it and go to the next example and see if that's one that you're interested in. Not only that, by doing that, you're going to see all the different problems you have access to. I also updated the my list of videos. So you now have another updated list that was updated late last night with all the titles I have on my YouTube channel. So you can look through there for problems that help you. Their titles are pretty self-explanatory, and then they got descriptions that give you even more information usually. So anyways, I'm going to put this off to the side and jump into chapter 6. So we've done more than enough really for chapter 5. I've worked way more examples than I normally do, even in my face-to-face classes, even though the 50-minute teaching schedule is not the ideal scenario. What I'm going to talk to you about is gravity. And in fact, chapter 6 is about Newton's law of gravity. And you might think, why would we even study Newton's law of gravity? We know that relativity has made that wrong. And in some sense, you're right, but in the most important sense, you're not. For instance, we were able to go to the moon without using general relativity at all. Didn't need to. If you wanted to pay attention to time, you had to take into account general relativity. So if they were doing signals or using time coordinates to the spaceship, then yeah, they'd probably correct that for they are probably correct that for general relativistic effects. But other than that, you really don't need it for the orbit. So Matthew asked, where is it going to be located? The extra credit, I mean, it's the description of it is in the video. So you actually have to watch the video, or at least fast forward it to that point where you see me write EC or extra credit on the side. I write it in red. And then the actual assignments to be turned in at the bottom of the week 5 module. You'll see it right below your 2 homework assignments. So here's what Newton did. So Newton said he was sitting in his apple orchard, basically, if you read his Principia, and I got a couple versions of it back here on my bookshelf behind me. But if you read it, it basically says I was sitting in my apple orchard and I looked up and saw an apple. And then at the same time, I saw the moon in the background, and he realized how the apple and the moon were the same, which is pretty absurd. But after I explain it, maybe it'll make a little bit more sense. What he means by that is eventually that apple is going to be so ripe and so full of water that its weight will exceed the capacity of the little stem to hold it, and it'll just fall. And he said, I suspect that force that's pulling that apple down to the ground is the same force that's making Newton's first law, which, you know, Galileo's law of inertia, be valid for the moon, i.e., the moon actually has a changing velocity. There must be a force causing it, right? And the reason why I knew the moon was changing velocity is because it orbits the Earth. So his plan was this. He said, okay, well, let's look. Here's the Earth. And the Earth has a radius, let's say just r. And then he said, okay, well, normally the moon would just go off that way at that point in the orbit and go forever. But because it doesn't, because it orbits instead, we know that it's actually accelerating towards the center of the Earth, right? And he said, well, that acceleration, I know, because, you know, I invented calculus and I'm the bomb. I know that acceleration AC has got to be equal to v squared over r. Well, we know that v is just 2 pi, if you assume circular orbit, 2 pi times the distance, i.e. the orbital distance from the center of the Earth to the center of the moon, over t. Well, he also was smart enough to know that this orbital distance d, which I'll draw in red just because I drew my little line in the way of it, that distance d is actually equal to 60 times the radius of the Earth. Okay, so you can go ahead and calculate that, and in fact, when you do that, you can find out that the well, you have to use the fact that the period for the moon is 27.322 days. So we'll say t equals 27.322 days. We know that d equals 60 times the Earth radius. The Earth radius, by the way, is approximately 6 times 10 to the 6 meters, which is a nice, easy thing to remember. But I'm going to try to get a little better result here by using the exact result. And that is the Earth's radius is 6.38 times 10 to the 6 meters. You'll see in your book it says 6.38 times 10 to the third, but that's in kilometers. Okay. So we should be able to now calculate the velocity of the moon. The velocity of the moon would be equal to 2 pi times 60 times 6.38 times 10 to the 6 meters, because that's the d. Whoa, wrong one. Sorry about that. It's 2 pi times the distance. Yeah. I did that. Okay, yeah. I forgot I put the 60 there. So yeah, it's 2 pi times the distance, and the distance from the center of the Earth to the center of the moon is 60 Earth radii. So that's why that works. And then I'll divide that by 27.322 days. But I have to have the right unit, so I'll use the fact that 1 day is equal to 24 hours, and that 1 hour is equal to 3,600 seconds. Okay, so let's do that calculation real quick. You can verify it on your side if you don't mind. That's 2 times 3.14159. I always use that many digits because I'm a nerd. Times 60 times 6.38 e to the 6th. And then I'm going to divide that by parentheses 27.322, 27.322 times 24 times 3,600. All that's in the bottom. That's why I put it in parentheses. I hit enter and I get 1.019. times 10 to the third meters per second. Anybody verify that calculation? Now we're going to take and calculate the centripetal acceleration. The centripetal acceleration is v squared over r. So I'm actually going to take that 1.0188, which is really what it was, times 10 to the third. Notice I'm carrying 2 extra digits now, meters per second. And we'll square that and divide it by 6.38 times 10 to the third, 10 to the 6th, excuse me, meters times, remember the radius of the orbit is actually the 60 times that. So I got to put the 60 in there. And let's see what happens now. So I'm going to take that velocity and we'll square it. And then I'm going to divide that by parentheses 6.38 e to the 6 times 30, or excuse me, times 60. And I get 2.71193, which really should be, I only did 2 sig figs there, so honestly I shouldn't be using any more than 2 sig figs. So it's about 2.7. All right, so he knew that was the acceleration that the moon would have to have, but he also knew the acceleration at r equals 1 Earth radius, okay, was equal to 9.80 meters per second every second, right? So he said, I wonder if this force happens to be a 1 over r squared force. And the reason why I wondered that is that's a common mathematical thing, but he also had been working with light, and light is found that its intensity actually decreases like 1 over r squared. And in fact, it's such an important concept that when Einstein was asked if he believed in ESP and telekinesis and stuff like that, he said, if you show me it obeys a 1 over r squared law, then I'll believe it's true. And by the way, no, it just doesn't. No one's ever been able to show it obeys a 1 over r squared law. So he says, I suspect then that the acceleration at 60 Earth radii should be equal to 9.80 meters per second over 3,600, because it's 60 times as far away. And if it's a 1 over r squared, it should be 60 times 60 times smaller. So that's 60 times 60 is what that 3,600 is. And lo and behold, when you do that, you get 2.72. Okay. So at that instant, Einstein, at that instance, Newton was the only person on planet Earth that knew why the moon orbited the sun, or excuse me, the Earth, and why the Earth orbited the sun and all the other planets. And in fact, what he ultimately said was that the force of gravity is equal to some constant we now call the gravitational constant times the product of the masses and inversely proportional to the square of the distance between them. And experimentally, it's been determined that G is equal to 6.67 times 10 to the negative 11th. You can tell the unit should be newtons meters squared per kilogram squared. And F acts along the line connecting the centers of mass of M1 and M2. And big and here is always attractive. Now, if we actually found a repulsive form of gravity, then we'd have to rethink everything. But so far, we've never found such a thing. So what Newton's law of gravity says is that the force of attraction between two bodies exists as long as the two bodies have mass. That the force will act along the line connecting the center of masses of the two bodies such that M2 is being pulled towards M1 and M1 is being pulled towards M2. And that's it. It's also inversely proportional to the square of the distance between them. So if I double the distance apart, I actually reduce the force by a factor of 4. If I triple the distance apart, I'll reduce the force by a factor of 9, so on and so forth. If I double one of the masses, I'll double the force. If I triple one of the masses, I'll triple the force. If I double one of the masses and triple the other mass, then I'll sextuple the force. Does that make sense? It turns out that law is exactly the same form of what we call Coulomb's law, which Ben Franklin had some work in discovering as well. And that is F Coulomb, just for the record, is equal to K times Q1, Q2 over R squared. So you can see Q's, which represents charge, plays the same role as mass in electricity and magnetism. There's actually an equivalent form of this for magnetism, but it's too complicated to write. R squared is the same behavior, but here's the crazy part. In this case, K is about equal to 8.99 times 10 to the 9th, not 10 to the negative 11th, 10 to the 9th Newtons meter squared per Coulomb squared. So later when we start doing electricity and magnetism and stuff like that, you'll see why we ignore gravity, because even if you just compare the constants, the force of the Coulomb force should be 10 to the 20th times stronger than the gravitational force. It turns out, though, when you actually compare things, like you compare the gravitational attraction between the proton and neutron, or excuse me, the proton and the electron and the hydrogen atom, F Coulomb over F gravity is on the order of, I seem to recall, 10 to the 44th. Okay, that's a calculation you should try, because all you need to know is Q1 equals Q2 equals E, which is 1.602 times 10 to the negative 19th. And then, of course, you can look up the distance, what we call the Bohr radius. That's a Coulomb, by the way. That's the unit of charge. And you can look up the Bohr radius, which I think is 0.511 times 10 to the, I think it's negative 10th, is the Bohr radius. See if I can even find it in your book. Yeah, I don't think it. Yeah, it's not listing it in your book, but it's something like that. But you can Google that if you want, Bohr radius in meters. Okay, it's usually given the symbol A or A0, something like that. And like I said, it should be in meters. But if you want to try that, I'll probably throw some extra credit at you if you want. I'll probably make that a little bit of a problem, sort of on par with a conceptual homework. So if you want to do that, this is extra credit. Any questions on that? All right, so that was a really big deal that Newton was able to find that. And in fact, he went on to actually explain, we will learn, for instance, Kepler's laws. And Kepler's law says, one, that the planets orbit the sun in elliptical orbits with the sun at one focus. That's a really big deal, because Aristotle taught us that the heavens were perfect. And the perfect shape is the sphere, ergo everything in the heavens must be spherical. Of course, if you attach that planet to a sphere, then it should be not orbiting the sun, by the way, it should be orbiting the Earth, and its path would be a circle. So a circle, again, being a perfect shape as well. So they expected the orbits to be exactly circles, right? Because the heavens are perfect. The ellipse is a bastardized circle, really. Okay, so that was a real smack in the face. The second thing is that the square of the period is proportional to the cube of the semi-major axis of the orbit. Okay, so the way you draw, for instance, in a circle, you could put a nail in a piece of plywood and pull a string taut and then tie a pin to it, and then keep that string nice and taut and keep that pin nice and vertical, and you'll trace out approximately a circle. Okay, if you do that with 2 nails though, and you make the string longer than the distance between the two, and you pull it tight like this, then what'll happen is you'll get an ellipse. So that's what an ellipse is. This is called the major axis. This is called the minor axis. And of course, half of it's a semi. So you can also put semi on the front. And that just means half. So this would be a semi-major axis. This would be a semi-major axis. This would be a semi-minor axis. This would be a semi-minor axis. Does that make sense? So what he's saying is, if indeed this is an orbit of a planet, then the sun might be there and nothing special will be there. Okay. Now, the other thing, that was the first law, is the planets orbit in elliptical orbits with the sun at one focus. And that's what these things are called. The plural is foci. And now if you take that same sort of orbit, I'm trying to draw an ellipse, it's not going to be that perfect, of course. And this is your sun. Let's say the planet is here on day 1, and day 30, it's here. Well, this is like a pizza slice that's short and wide, right? Whereas if you went out here and tried to do a pizza slice with just the same amount of cheese and crust, or actually the same amount of weight, let's put it that way, then since that pizza slice is so long, it can't be nearly as wide. So in fact, what that's saying is this: if this is day 1 and this is day 30, then this area A1 is equal to this area A2. That's his second law. So the sun, the planets orbit the sun in elliptical orbits with the sun at one foci. The second law is they sweep out equal areas in equal times. That's why the planets slow down when they're far away from the sun and speed up when they're near the sun. And then thirdly, he said the square of the period is proportional to the cube of the semi-major axis. Okay, the semi-major axis is essentially the average, because notice this is called perihelion. That's when the planet is closest to the sun. And this is called aphelion. And that's when the sun, the planet is farthest from the sun. If you take the average of those two, then you'd add this little distance plus that distance, and then you divide it by 2. And lo and behold, what you get is half this whole distance, which is a semi-major axis. So that's why I can say the semi-major axis is essentially the average. Okay, and this is the period, the time required to go from one spot in the orbit, say here, all the way around to here. So that's his third law. This is his second, and this is his first. Okay, so those are Kepler's laws. When Newton discovered a formula for gravity, he immediately was able to prove these. He found that this was the result of the mechanics of the force law being 1 over r squared. In fact, he was able to show that any 1 over r squared, or if you try to make a stable orbit, an orbit that will repeat itself in time, there's only 2 forces in nature that actually work. One is the 1 over r squared law, which is what gravity is. And the other one is F equals kx, which is the spring law. Any other force cannot make a stable orbit whatsoever, and he proved that. Okay. He also proved that when you have an orbit, it can be only one type, and that's called a conic section. So what do we mean by a conic section? Again, we're approaching time. So a conic section is, you imagine two of those little water cups you get at gas stations and service stations and stuff like that, tail to tail, you know, the two little cones. And if you slice it this way, then it makes a parabola. If you slice it vertically, say right across here, then it makes a hyperbola. Like that. Oops, like that, sorry. If you slice it horizontally, it makes a circle. And if you slice it at a slight angle, it makes an ellipse. So the only choices are ellipse, circle, hyperbola, and parabola. So Newton was able to show all that. He showed this was due to conservation of angular momentum, and he showed this was due to conservation of energy, basically. So that's it. We have gotten a lot done for the first day of chapter 6. I suspect we might be able to finish it on Monday. If not, we'll definitely finish it by Wednesday. So make sure you guys get your homework done. You got, I think I got one homework assignment due Sunday and another one due Wednesday, and then there's that extra credit thing that's available to you guys that I think will be kind of neat. So y'all have a good one, and call me if you need anything. Yes.
Yes, Professor, can you actually scan like the page? Do you have a scanner and I kind of upload it so we could see it more clearly?
Yes, I do that every time. That's where the Google Docs is. If you look on my Canvas page, it's like the third module down, and it says important links and documents. There's a link to my Google Docs page, and all of the notes are there.
Okay, thank you.
They're listed by date. Like today's will be 092421. So if you just do a search for that, you might see that, and you might see, you know, a different class. Like you might see a D01B, which is your class, excuse me, but you also might see a N05B, which is the next class. So you just want to make sure you get the right one. But other than that, the name will end in.
Okay, all right.
Okay.
And then Professor, are you gonna post the lab for today?
Yes.
I just wanted to look at it before class.
Yeah, I'll post it right after I get off of here.
Okay, thank you.
No problem.
Okay, bye.
Bye-bye. Anybody else?
That's so strange. The notes became crystal clear there for a second.
It keeps telling me that my resources are being used, so it's like bad photo, but I literally don't have anything else open. I think Zoom just uses a lot of
it's got to be the internet connection. That's the only thing I can imagine.
Yeah, that stinks. I was doing it with this a lot closer, but that wasn't necessarily doing any better. I might try that again now that I'm saving it to my local hard drive instead of the internet. Maybe that'll help.
Who knows? Anyway, thank you.
No problem. Have a good one.
Professor, I have a quick question about one of the previous lessons. I was wondering if you could help me out.
One of the previous, what's that? You said one of the previous lessons? Okay, yes. How can I help you?
Yeah, I'm just a little confused on how tension works, because I was looking at the I believe it was chapter 4 homeworks, and it's talking about tension with all the ropes, and I just can't understand it.
Yeah, that is it's kind of a weird thing, but when you're using it like in an Atwood machine, you got to remember that the tensions on the two sides have to run towards each other, which seems kind of weird. So one thing I'd tell you from the get-go is to think from the perspective of the object that's on the rope. So for instance, when you're looking at a Atwood machine, hopefully you can picture that in your head, right? An Atwood machine.
Yeah.
Okay. Actually, I'll go ahead and draw it. What the heck? So if you're thinking like this, and let's say this is a big M, and let's say this one's a little m, then from this perspective, you say, oh, wait a second, this is a really big mass. And on the other side, I know there's a really small mass that's not going to be able to hold me up. So as a really big mass, i.e. me on a train car or whatever, I know that I would try to fall at a rate of 9.8 meters per second, but that stupid tension is pulling me, right? So then immediately is slowing me down. So immediately you get the idea that over here, the tension is this way. And then if you jump to this one and say, wait a second, we're a lot smaller mass than that car over there. So yeah, I would be trying to accelerate downward, but this stupid rope keeps pulling me up. And then all of a sudden you've got the direction for the tension correct. Now, the other thing is also weird. We'll eventually go to where we start to study the pulley, and that's where the tension is going to come in again. And if you're the pulley, you're thinking, hey, I'm trying to rotate this way. So it seems like this one's fighting me. So I'll call this TL just to separate them. It seems like this one's fighting me. So now this TL is pointing down, whereas it feels like this one's trying to help me. So this will be TR for T. Actually, I did this completely backwards. But anyways, we're going to do that and pretend like we're looking through our paper. So that's one lesson I want to give you right from the get-go, is that will help you. I know it always made no sense to me, the directions that tensions were when I first saw them. But then when I started thinking as this, yeah, this mass right here feels that rope pulling up on it. And this mass right here feels that rope pulling up on it, right?
Right.
And then I think as the pulley, I was like, wait a second, the pulley's trying to rotate this way. It feels like this one's helping them and this one's fighting it. Once you get all that in your mind, then the directions make sense. Now, beyond that, do you have a specific issue, like a specific problem you can share to let me help you with it?
Yeah, I could look one up really quick, and if Brandon or Richard have any questions, they can do that while I'm trying to pull one up.
No problem. I just said it where you can share, you can share your screen. Brandon, Joshua, either of you guys have questions? Are you guys there, Brandon, Joshua? In the chat, yes. Sometimes people come on and they like get disconnected, or they just walk off and forget they're still online.
Yeah, it's a lot easier to skip class online now.
Okay, so this is actually, I went ahead and moved the camera to being closer. Is that more visible, easier to see?
Oh yeah, that's perfect.
Good. Trying to get it squared up too. I want it to be just wide enough for the whole piece of paper to fit.
Yeah. All right, I'm gonna share
Okay.
my screen now. All right, there we go. So the thing I'm confused about is just how this part works. Because I did
Yes.
this was right, but it was a lot of work to try and figure those out, and I'm still confused.
Yeah, so yeah, this one was kind of a neat problem. I liked it. It said, what is the magnitude of FAD on the downward force on section A? Okay, so the downward force is on section A is basically due to sections B and C. So let me see in terms of tension. Okay. Let me read the opening question too. To understand the concept of tension and the relationship between tension and force, this problem introduces the concept of tension. The example is a rope oriented vertically that is being pulled from both ends, FU and FD, with U for up and D for down, represent the magnitude of the forces acting on the top and bottom of the rope, respectively. Assume that the rope is massless, so its weight is negligible compared to the tension. This is not ridiculous approximation. Modern rope materials such as Kevlar can carry tensions thousands of times greater than the weight of the tens of meters of such rope. Consider the three sections labeled A, B, and C. At point 1, a downward force, FAD, acts on a section A. At point 1, upward force, FBU, acts on section B. Gotcha. At point 1, the tension in the rope is T1. At point 2, a downward force of the magnitude FBD acts on the tension B. At point 2, an upward force magnitude FCU acts on section C. And at point 2, the tension of the rope is T2. Okay. All right, so what is the magnitude FAD? So that's the force acting downward on section A, basically. And that is the tension 1, because they said the at that point, the tension of the rope is T1. And it's got to be downward, yeah. So that makes sense for that one. What is the magnitude FBU of the upward force on section B? Okay, so the upward force, that should also be T1 for the same reason, basically, that you see as we did with my particular rope. We had this tension that was pulling up on the little mass actually pulled down on the pulley. So it's literally the same in magnitude. And that's, Newton's third law is more or less giving you that. Newton's first law would be able to tell you if it's not accelerating that all the forces add to be 0. Newton's second law could tell you what the acceleration is if you knew the net force, but Newton's third law identifies the forces as equal but opposite. Does that make sense?
Yeah, it does.
That is the wording of that made it somewhat worse. And in reality, the tension at 1 would actually be a little larger than the tension at 2, because the rope at 1 is a little longer and therefore has a little bit more mass. So that tension at 1 would have to be able to supply the force FD plus lift the rope parts B and C. Whereas the tension at 2 would be required to supply FD, but would only be required to carry additionally the weight of section C of the rope, not B and C. You see what I'm saying? So that's what happens as you cut it up into small pieces and start to think about, well, what makes them change? And that's in fact why I had to use TL and TR on here, even though I did it backwards. I had to do that because the tension in the pulley or the tension on 2 sides of the pulley will be different, because this side's got to not only lift the weight, it's also got to turn that pulley against its friction and its own inertia.
Okay, thank you so much. This is really
helpful. That helps. I know I probably didn't say much for you, but hopefully it made it make some sense to you.
Oh, it did. Thank you.
Okay, thank you. Have a good one, Joshua.
You too. Bye.
Yeah.